Numbers are a critical part of the way we understand our world. Numbers are among humanity's oldest and greatest tools. In this video series, I would like to explore numbers, but not just any ordinary numbers. We are going to explore big numbers. Last time, we described moderately large numbers as we worked our way up to 1 Google, before moving on to the massively large Googleplex, a number so big that we cannot fully visualize it with the materials in this universe. This number will now be our starting point as we begin to build numbers a little more quickly. As large as Googleplex is, we don't have to go much further to find a much larger one. In 1933, Stanley Skewes was working on an unsolved problem involving prime numbers. Although he didn't find an exact solution, he was able to find an upper limit to the problem. This is Skewes' number, and it is much larger than 1 Googleplex. But Skewes wasn't the only one working with big numbers. Hugo Steinhaus was a giant in the mathematics community, made major contributions to geometry, as well as being one of the founders of game theory and probability. Steinhaus also developed a unique notation for large numbers. This is called the Steinhaus polygon notation. Here, a triangle is used to describe a number that is raised to the power of itself, and 2 squared is equal to 4. A square is used to describe a number that is inside that number of triangles. And as we saw before, 2 squared is equal to 4, while 4 to the 4th is equal to 256. The last shape Steinhaus used was the circle, which describes a number that is inside that number of squares. 2 in a square we have already seen, and we've calculated as 256. 256 in a square is the same thing as 256 inside 256 triangles. Evaluating the first triangle gives us 256 raised to the 256. This is roughly equivalent to 10 to the 617. Evaluating the next triangle gives us this number raised to itself, or about 10 to the 10 to the 619. This is already much, much larger than Googleplex, and we still have 254 triangles to go. 2 in a circle was termed a mega by Steinhaus, and is vastly larger than Skewes' number or Googleplex. But there's even more we can do with this polygon notation. An Austrian-Canadian mathematician by the name of Leo Moser built upon Steinhaus's work and decided it would not do to stop at the circle. A triangle gives a number to the power of itself. A square is defined as a number inside that number of triangles. And now the pentagon is defined as a number inside that number of squares. But now we can go even further. A 2 inside a hexagon would equal 2 inside 2 pentagons. The 2 inside the inner pentagon is mega, which means we now have mega inside a pentagon. This translates to mega inside a mega number of squares. And that's only starting from a 6-sided shape. Each time we increase the sides of the polygon, the resulting numbers explode in size, dwarfing the numbers that came previously. So what happens when we reach a polygon with 100 sides? Or 1,000,000 sides? How about a Google sides? Moser decided to define an even larger number. A 2 inside a megagon, where the number of sides is equal to a mega. That means this massive number that is already stretching our comprehension, that is the number of sides of this polygon. Moser's number is so massive we barely have the language to describe how much notation we would need to describe how big it is. So how can we get a grasp on how enormous this number is? And how can we describe anything bigger? For that, we will need new notation in another video. We have expanded so far beyond numbers like Google flags that they seem infinitesimal by comparison. We've reached a dizzying height in the progression of numbers that going any further hardly seems possible. And yet there is still so much more to come. So please join me for the next video where we explore big numbers.